Hey folks, Matthew here with Disaster Area Designs, working on this QCONNECT. So we started building this on Instagram earlier today, and Instagram Live is great. I love Instagram Live, but I also wanted to be able to put the camera in landscape. So this is landscape set up, and right now I'm trying to get this talking to my Mac so I can see on the monitor what's actually in frame or not. So here we go. You go away, not you. I'm actually just talking to myself. Okay, so now I can see what's on the camera and what's in frame. All right, let me add a little more light here to the situation. There we go. Wonderful. Okay, so been live for a whole minute and no one's watching. That's okay. I don't mind. This is also for posterity, so hopefully we'll be able to put this on the channel and have this be something that everybody can watch later. All right, so in the Instagram Live video, I put up, we got the board ready. We added the display driver chip, which is this guy, the ARM, which is this guy, and then the power regulation circuitry. So there's a 5-volt regulator here, a 3.3-volt regulator here, which is this little guy right here, and a couple of caps, 3 caps, the crystal, and the 2 protection diodes, USB port, and the fuse. So this board, the bootloader loads, and we can program it over USB. So this guy is now ready to get the rest of his components populated. So we've got a few things that have to go on here, and let me run them down for you. All right, first up, we have 2 shift registers. These are 74HC595s. They're serial in and parallel out. So basically, we can connect 3 wires to these guys and get 16 outputs. So we send them bits of data, and they will turn on their outputs. And so it lets us get a nice breakout. So instead of having to run 16 wires all the way over here, I only have to run 3. So that's actually a pretty nice way to do it. Also, they can act as level shifters. So if I need to interface with something that's 5 volt, for example, and then this guy only puts out 3.3 volts, I can use these guys as a level shifter to get a 5 volt signal or multiple 5 volt signals out of a single 3.3 volt input. I have 3 quad, these are quad tri-state buffers. These are going to be sending the signal to the 8 jacks here. So each of these is 4 buffers, and so this one is going to do outputs A and B, this is C and D, and this is E and F. So these will handle the 6 black jacks on the QCONNECT. And then the X and Y, which are these guys here, they're connected directly to the processor. So they have some special powers that the other ones don't have. And that's okay, I don't really mind. Let me move this guy so he's a little more in frame. There we go. Okay, so we have to add a diode down here. We have to add a bunch of resistors. We have to add an optocoupler, which goes here, OK1. This is a buffer. It's just a non-inverting buffer. It's 74 LVC G17. So it's basically like a 7417, but it's a single buffer rather than a hex. Okay, so none of these guys are particularly sensitive to what order we do them in, so I'm just going to reach in the bag and see what we got. Okay, so first thing up is 74HC125AD. So these are SSOP. These are SSOP 14 pin. So I need 3. Good, because I have 5. Okay. And then always put your stuff back in the bag so you can figure out what the heck it is later. All right. So I've added some flux to the board. I'm using Kester 951 flux in the pin format. I'm just going to add a little bit of that. I don't ever think you can have too much flux. And so then we're going to identify pin 1 on the chip, and pin 1 is the upper left pin. In our case, let me get it in frame. In our case, it is actually the lower right pin because we're mounting these upside down. Can you guys see that little dot there? There it is. All right, so that little dot is pin 1. So we're going to put pin 1 here, and then we're going to put a little solder on our iron. And yes, I know I say solder, not solder. That's okay. I can say it any way I want because it's my channel. All right, now I'm going to line it up, and please forgive me if you see the top of my head or my ear or something, but I do need to be able to see the top of this. And I'm just going to put a little bit of solder on the pins, and I don't particularly care if I don't get it on all of them or if I get it on there like a little wonky or anything like that. It's okay. All I'm trying to do is get a little bit of solder on there for a mechanical bond. I just want to make sure that it doesn't move and that none of the pins are actually touching each other or touching the wrong pin. So if it's on there a little bit crooked, it's okay. All right, so that one looks good. I'm going to take some solder and I'm going to flow on the other side. And even though I soldered those two pins together, you can see there's a solder bridge there. That's okay. We're going to go back and fix that later. Right now, I just want it to stay on the board so that I can go back and do all the detail work later. And I'm going to repeat that for the other two gates here, these other two tri-state buffers. So what is a tri-state buffer and why do we care about it? Well, normally TTL logic, and that's what these are, that's transistor logic. Normally TTL uses an output configuration called a totem pole, and that is basically a couple of transistors that work together in tandem, and one's job is to pull up high and the other one's job is to pull down low, and they're controlled inside the chip by some other circuitry, resistors and diodes and other transistors, but their whole job is to provide a bunch of current to the output when needed. So a transistor or logic chip, TTL chip, can sink current, meaning it can allow a path for current to go to ground, or it can source current, meaning it can supply current to a load. So if you have an LED, as an example, an LED is a load. It is something that takes power and does work, so it's a load. You can actually take your, so now I'm just going back and cleaning these up. You can take your TTL logic chip, like a 7414, which is an inverter, hex inverter, and you can actually hook it, the LED, to one of the pins on one end and ground on the other end, and if you get the polarity right, you can actually turn the LED on and off by supplying its current through the logic chip. If you wanted to work the other way, you could actually do it in reverse, and you could put the LED between 5 volts or 3.3 volts and the pin, and you could have the TTL chip connect it to ground. So either way will work on a TTL chip. Well, the problem with the TTL chip is that its only two states are high and low, basically 5 volts and ground or 3.3 volts and ground. What we're trying to do with the QCONNECT is we're trying to use these chips to turn the serial signal on and off to the outputs. And in order to do that, we have to be able to connect the signal to it and disconnect the signal from it. There's a couple pedals out there, most notably Chase Bliss pedals, who use they use the tip of the jack as the tap tempo, and then the ring is MIDI. The Alexander stuff, the Merit stuff, the Empress stuff does not do that. It's basically the tip is the MIDI and the ring is also the MIDI. What you run into on the Chase Bliss stuff is if you end up pulling that tip high or low, then the pedal thinks that the tap tempo is being held down and it acts strangely, so it's bad. Okay, so we got all those guys on there, and I was able to use my soldering iron to clean them up so that now they're only soldered where they need to be and I don't have to worry about them. All right, this is my buffer. The MIDI output's a level shifter. Let's do these guys, this guy next. This is my optocoupler, and these are white because they're fancy. These are HCPL 0453 made by Avago, which used to be Hewlett-Packard. Basically, Hewlett-Packard is in the habit of, like a lot of large companies, of spinning off some of their brands. Like, for example, Agilent used to be HP. So I have an HP, what is it, a 34401? I have an HP multimeter, like a really nice multimeter, a big one like like this guy, like that's a function generator, but I have a big multimeter that's roughly the same. It's a big bench multimeter. Like, you could not take it on a job site. It's enormous. But what's cool is it has GPIB, so you can hook it up to a computer and you can do automated testing with it. And that's why I had it in the first place. I worked for a company that did automated testing, and they had one that failed calibration, and they didn't want to pay to fix it. And so I took it and I fixed it, and then I took it to my buddy at Precision Measurements, and he calibrated it for me, and it's fantastic. It's also very impractical for a lot of the stuff that I do, but it's a very expensive meter, and I was glad to get it for basically free. So, but the one I have is an HP, but all the ones that are sold now, and they're exactly the same, are called Agilent. So there you go. All right, so I just actually broke this board off here by accident, but that's okay because it needed to come off anyway. All right, so HCPL 0453 is now on. It looks good. All right, so I got a little bit of solder schmoo on that last run here. Let me clean that up. All right, so you might ask, why am I streaming this live? Because this is the most boring thing ever. I've been at it for 12 minutes, and I don't think anyone has seen it, but that's okay, because I have to do it. This is part of my job that has to get done, and if you're watching or you're not watching, I don't really care. If you weren't watching, I would be probably watching Back to the Future while I did this. But due to copyright concerns, I will not be watching Back to the Future while I do this because I'm streaming. So, okay, so that guy's all done. Let me add a little solder to this tab. I dried him off a little bit here. So let me solder this a little bit. Boop. Okay. Now I see why Ben Heck makes weird noises and sings when he does this. It does kind of get lonely in here. All right, diodes, don't need those. 125s, regulators, BAS 40s, shift registers, and what's this last one? EPROMs, okay. All right, these two are the last chips. We have three things we need to put on the board. Actually, four, because there's two of these shift registers. So these are the aforementioned shift registers. Oh crap, I only have two of these left. Well, let's hope we don't mess them up. All right, 74HC595D. Grab these. All right, now these are the aforementioned serial in, parallel out shift registers. Little flux. Now these go on the normal way. They are 16-pin chips. Most 74 series logic chips are 14-pin. That's kind of the standard. So what they'll do is most of them are 14-pin. So what they'll do is they'll kind of pack extra stuff in there until they hit 14 pins. So while you could have, you know, a quad buffer or a dual buffer or something, what they'll do is they'll keep adding buffers until they run out of pins. So your typical 7400 series buffer is a 14-pin, but it's a hex buffer, so it has 6 buffer sections in it. And basically, you need 1 pin for 5 volts and 1 pin for ground. It's VSS and VDD. And then all the other pins get assigned to whatever function the chip has. Where that falls down is something like a 74HC595, because you need power and ground, VSS and VDD, and then you also need the clock input. So you have a clock input, and you have an enable input, and you have a data input, and then you have 8 outputs, and then you have a serial data output. So you have kind of an extra pin that lets you link them up. So your nice 8 pins, your 14 pins now has to be 16 in order to fit all your functionality on there. So this is an oddball 7400 series chip because it's a 16 pin instead of 14. And now you probably don't care. You're just watching me solder. That's okay. I see there's one person on this stream. So one person on the stream, I hope you're having a great time. I know I am. All right. So what I'm doing here is, you can see I have these, I drag soldered these, so I just soldered a big blob of solder all the way across, and I have several solder bridges. So what I'm doing is I'm heating them up, and I'm carefully drawing them away from the pins, and the solder really wants to stick to my iron more than it wants to stick to these pins. So I can just kind of pull it away like that. Let me zoom in more closely so you can see what I'm doing here. And I apologize for the lackluster video quality. This is an iPhone 6 in a stand, but hopefully it's enough. I'm having a great time too. All right. So this is an iPhone 6 in a stand, and the video quality is okay. It's not great. Like, would it be better with like a G7 or something? Yeah, of course it would. But I'm also doing this in the back storage room of my shop here. So not really a priority for the excellent video quality. On this buffer, and then we're done. So EEPROM. EEPROM is a tiny little guy. See these guys here? 24 LC64 FTI/OT. This is an SOT 23 parts, 5 pins. It has VSS and VDD. It has a serial data and a serial clock line. And then it has a write protect. And the write protect is a bit unusual because it does not actually write protect the whole chip. It only write protects a certain bank. And so what it lets you do is it lets you write stuff to part of the chip. I think it's the bottom half. I'll have to look at the data sheet to be sure, but it lets you write protect a portion of the chip so that you can put stuff that needs to stay in there, and then you can still write to the rest of it. So it gives you a more granular write protect than just all or nothing, like in an EEPROM, like in a, you know, a parallel EEPROM, like a 27C256 or something like that. It gives you the ability to write protect part of the chip, probably the only part you care about. All right, you guys are going to hear a weird noise. That's my desoldering iron. You know, I've been hearing that noise. I've had this desoldering iron now for, well, let me put it to you like this. I had it, this exact same one, at a job I worked back in 2004, and it was already old then. And then it belonged to my boss, and he quit and went somewhere else, and I quit and I went somewhere else. And then we kind of met up again later, and by the time we met up again later, he was not using it anymore, and I needed it. And so he sold it to me for a very decent price. He's a very decent fellow. I love him a lot. I miss working with him, but we can't both be the boss, right? So I decided I would rather be the boss. We have a second person joining us. Hello, second person. I hope you're enjoying yourself. This is a live stream about soldering a prototype board. So this is a bunch of surface mount soldering. The next thing we're doing, and I hope you guys can all hear me. I've got our lavalier mic on. Hello. Hello. I have the lavalier mic on, so the audio quality should be a bit better than just the phone in the room, but it's also not going to be as good as if I were doing a voiceover with a condenser mic or something. I do have a condenser mic, but I'm live streaming this, so we'll just go with that. All right, so this last chip is a 7.4 LVC, what is it, 17? 7.4 LVC 74 LVC 1 G17. And what that means is it's the 74 series logic, but the LVC is like low voltage compact or something. Basically it's 7400 series logic, but it's capable of working down to 1.8 or 1.2 volts, very low voltage, and it's a single gate. So unlike a 7400 series chip where they're going to pack as much in there as possible to use up all 14 pins, on this one they're just going to give you exactly enough pins to do the job and no more, because now it's more about saving space than saving chips. Back in the day it was about saving chips, and now it's about saving space. Pardon the chewing, the masticating noises, as Big Clive says. But I am chewing. I have a lovely cup over here full of soft drink and ice. And one of my many faults is that I like to chew ice. My dentist says it's terrible for my teeth, and I believe him. But I can't stop chewing ice because, well, I don't want to stop chewing ice. All right. All my chips are placed. All my integrated circuits are placed. And my display board actually is complete. So I can kind of put him to one side. He's actually complete and he's done and dusted. So I'm just going to trim these tabs. I hope I didn't tear a trace there. No, I'm good. All right. So these are my cutters here. These are my good cutters. These are Knipex. These are fantastic. They're very, very good. They'll cut iron up to 1.2 millimeter diameter and copper up to 1.6 millimeter diameter. I don't know what that is in real numbers, but it's pretty big in terms of wires. You can cut steel with it, but mostly things like resistor leads is kind of where you want to be. All right, so chips are done and dusted. I'm going to put this bin away. I'm going to grab these caps out of it. All right, so next thing I'm going to do are the resistors. All right, chewing ice is life quality. Man, you have no idea. All right, this is going to look bad because it's Mountain Dew, but I have a machine that makes pellet ice, like Sonic ice. Man. Oh, so good. It's crunchy. It's chewy. Doesn't hurt your teeth because you're not having to fracture a big lump of ice. Okay, so resistors and capacitors. We're going to do the resistors because they're different values, and then we'll come back and do the caps because they're pretty much all the same value, and it's not as important. Let me put some of this stuff away. All right, and we're going to need 4.7K, which is this one here. Let me zoom out. All right, 4.7K here. We're going to need 100K. We're going to need 100 ohm. We're going to need some more 100 ohm, I think. Maybe not. 100 ohm. What else are we going to need? 220 and 330. And this will be the 5th or 6th QCONNECT prototype I've built. I did 3 for NAMM, and then I did another 2 for the second board revision. And I'm going to build this one, and then I'm going to build one more on Wednesday. We've got another board coming. The layout is pretty much the same as this, but I've moved a couple of the pins around. This one is just to see if everything works, and one Wednesday will be for all the marbles. So what I'm going to do is I have all my resistors here, kind of mise en place style. You can't quite see them because of my camera mount, but I have all my resistors there, sort of, you know, again, mise en place. Any of you guys cook? Well, that's kind of what it's like. Okay, so break off a piece of solder. What I'm going to do is I'm going to solder all of the, I'm going to break this board off now. I'm going to solder all of the pads on one side, and then I'm going to heat up that pad, each pad. I'm going to place its associated component on the pad, and then I'm going to remove the heat so that the solder that's on the pad holds the part down. Now, the reason that you do one pad and not both pads is because if you do one pad, you can heat up the one pad and the other pad is still flat. If you heat up both pads, then when you're trying to place the component, it won't sit flat down on the board versus if you place it on there like this. So this is the upper jack board, and these resistors here, so this is the back of the jack. So this is tip, ring, sleeve. Sorry, tip, ring, sleeve, sleeve, ring, tip. So this goes to the sleeve, it's ground. This one is 100K, 100 ohm, 100 ohm. So it's all the way across, they're all the same. So 100K, 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 100, 100, 100, 100, 100. So these 8 are 100 ohm. So we're going to need 4 100K resistors. So we'll do them first. And I have cut tape here, so this is tape off. I have a reel in the drawer for things that I use a lot. Reels are pretty cheap for resistors. Resistors are a couple cents a piece. They're not, like if you lose one, as long as you have another one, you're not really losing a bunch of money. All right, so if I had heated up, if I had put solder on both pads, then when I put the part on there, it would kind of be like imagine imagine my fingers are the two solder pads, right? And they are both covered in solder, so they're both kind of rounded, domed. Here's my resistor, and I put it on top, and I solder one. The solder is going to flow, and so it's going to do this. And then when I solder this other one, the solder is going to flow, and it's going to do that. It's going to move away. So I won't be able to get a good solder joint. So the only way around that is to just do one at a time. So I heat up one solder pad, and I'll put the part on there. And I'll just kind of slide it on there. And now it's flat on the board. So here's my part, and I picked it up, and now I'm going to turn it, and this is my little party trick. It's in the tweezers, and now I turn it in the tweezers like that, so it's facing up, but I don't have to put it down and try to flip it. I can actually turn it in the tweezers in my hands without dropping it. And that, my friends, is some tweezer skill. I'm sure there are plenty of you out there that can do the same, but I always think it's impressive when I do it and I don't break anything or drop anything like I just dropped that. Now you can see on my desk here I have a bunch of little solder goobs and whatnot, dirt and fiberglass chunks, and I think it's pretty funny that a lot of my parts are the same size as my solder goobs. Okay, so 100K, those are done. I'm going to need a couple more for the upper board, but I'm going to do this lower board now. All right, now I need 8 of these 100 ohm resistors. I actually need a ton of 100 ohm resistors. I need 2 for every output. So I need 16 of them total. I need 8 here, and I need 8 on the other board. I'm also going to need to put a diode on this board, and I unfortunately neglected to do that before, so we're going to have to go back and put the diode on. Not a big deal, especially because we haven't put anything on the back of this board, so the board will still lie flat. A lot of surface mount soldering is hampered if the board won't sit flat, because a lot of what you have to do relies more on gravity. If you're doing through-hole parts, the parts generally, they go through the board, and then you can use the leads, like the wires that connect the parts. You can use them to kind of pin the part into the board. So it goes in, and you can pull the lead out through the hole, and then you can bend it over or move it to one side. But with surface mount stuff, you really can't do that because nothing goes through the board, or very few surface mount things have anything that goes through the board. Connectors maybe being the one exception, and that not all connectors. So with surface mount stuff, it's a lot of gravity work. All right, so I need to put a diode right here. Let me grab my box of parts. Let's see, PMEG 3000 or 4000. What have I got? PMEG 4005 CT. That is a low dropout Schottky diode. Look up Schottky, S-C-H-O-T-T-K-Y, Schottky diode, for a further explanation of why they're so amazing. Schottky diodes. Quantum tunneling. Schottky diodes involve things that we don't actually understand. They're just magic. Like Thor's hammer. Okay. Anybody else upset that Thor's hammer turns out to just be alien technology rather than actual magic? It seems like a ripoff. Okay. Diode is placed. Sorry, I did that mostly off camera. All right, I'm going to go back on this board, and I'm going to just touch everybody so that everybody is now soldered. We try to do this in frame. It's hard because as I zoom in and out, I don't necessarily know where my frame is. All right, I have turned the board so that I'm operating perpendicular to the side of the part, because I'm trying to get my iron parallel with the edge, like that. Let's get that down. Okay, these are going to look real shiny and gross because of all the flux from the solder. We're going to go and wash them when we're done. I'm not going to put you guys through the whole thing because I don't even know if this is going to work, and we're just going to get everybody on here, and then we'll go back and we'll wash it later. Okay, so the upper board is done. He needs, you know what, let's go ahead and do the connectors on this one. No, let's go we'll do the connectors later. Okay, let me finish the resistors on this. Okay, so this is the main logic board. These up here are 13, are 14, are 15, are 16. Those are 100 ohm. These are caps, Charlie 8, Charlie 7, they're 0.1. Okay, so we got Charlie 13, it's a 0.1, Charlie 14 is a 0.1. These are all decoupling caps. So these are all 100 nanofarad or 0.1 microfarad. Our 18 and 19 are 4.7K. He's 3.3K, 0.1, 4.7K, 220, 220. All right, this one's got a little extra solder on it, so I'm gonna forgive the noise, please. All right, and then these guys here, this is the last string of resistors, but we're gonna do them first. 100, 100, 100K, 100K, 100, 100, so they're symmetrical. These are the same resistors that would have been, that we just put on the other one. They serve the same function. The difference is that since this board will be assembled by a robot later, when all the surface mount stuff to be on the same side, so because of that, some of the parts go on different sides of the board when it's done, so that in production they'll all be on the same side of the board. It's complicated, but basically we're going to take the small board that we broke off earlier and we're going to end up flipping it around to connect it to the big board, which we're working on now. So we'll miss the two in the middle, and we'll do these two on the outside, and then we'll go up there and do those 400 ohm resistors. The 100K resistors are pull downs, and they are used for Maris and Alexander and Empress, so that when they're set to MIDI, this MIDI that comes back on the ring is pulled to ground and we don't get echoes. Quarter-inch jacks sometimes have their contacts very close together, especially inside the plug. If you ever look inside a quarter-inch plug, a TRS plug, like one of those pancake ones, you'll notice that the wires that connect the tip and the ring are really close together on that central stem. And that can cause problems if you have data going back and forth, especially if you have a high impedance input or something where it's easy to pick up signal. So sometimes it gets a bit gnarly, you have to watch it. So those resistors are there just as a little weak pull down to make sure we don't have any problems. All right, we'll put the rest of the hundreds back in the drawer. Just like pick these up and we'll put those away. We're done with hundreds. Hundreds. All right, so now we need 100K. We need, where's 100K? There. We're going to need 200K, and then we're done with those. 100K. And these are labeled 104, which is 10 times 10 to the fourth. Or I guess 1.0 times 10 to the fourth. There we go. Okay, that's 100K. All right, so now let's see, 4.7K. 4.7K. We need 3 of these. So there are 2 for the I2C pull-ups. Those are the 2 that go on the lines that talk to the EEPROM and the display and what else? I think that's it in this one. EEPROM and display. And then there's one that is the collector resistor for the opto coupler, the transistor in the opto coupler. So those guys, and then one goes right here. Let me turn the board. So this one goes right here. Hopefully it's not too goobery. Okay, good. Okay, what value is this guy? Who are you? 100K. All right, did I get all these in the right spot? 100. Nope, that's 101. That's not going to work. That's going to be a very short trip for that guy. All right, he needs to go here. And he needs to go here. Okay. Okay. All right, so let's see. 101, 101, 101, 101, 101, 101, 104, 104, 101, 101, 472, 472, 472. Okay, so we need 220 and 330. So we only need one 330 ohm resistor, and the reason we could use a 220, but the reason I use a 330 is because I've found that these parts like to have a little bit less current going into them than this rated spec. It's not a big deal, but it definitely helps them work better with faster signals like MIDI clock. We've had some issues on some parts. sometimes these even need to be 1K when we've used them with 5-volt lines. Okay, so that's 330. Let me put 330 back away. And then the other two over here for this output buffer need to be 220. And that's just the regular spec. It means that we've got a 5-volt output and you got 220 across it, you get 1 milliamp. So, okay, so 220, 220, and that's part of the MIDI spec. That's where we interact with other stuff. Okay, so is that all my resistors done? 330. Yeah, that's everybody. All right, I'm going to solder the tails of the resistors while I'm in here so I don't miss anybody. You. Okay. So I'm basically going back and I'm soldering the side of the resistor that I had not previously soldered, which is great. There we go. Okay. All these guys. When I first built this, when I built it on the Instagram live stream, I had put in just this one single 10K resistor. And the reason for that, that is the pull-up for the reset line. And if that is not pulled high, the reset line will be left floating, and the chip may or may not ever go into or stay out of a reset. So it's very important for that guy to be done. All right, so all that's left are 0.1 caps. So I need 1, 2, 3, 4, 5, 6, 7, 8. Looks like 8 of them. All right, so these are 2.2s. All right, so I have a drawer here of 100 nanofarad caps. 100 nanofarad, it's the same thing as 0.1 microfarad, tenth of a microfarad. So nanofarad is a unit that we don't use that often in the US. We use microfarad and picofarad a lot. A farad, it's named after Michael Faraday, is a very large unit of capacitance. It's basically 1 million microfarads. Now, anybody who has ever worked in car audio knows that you can go down to your local car audio place and you can buy 1 farad capacitors. Oh yes, no problem. But for electronics work, they're fairly rare. I've used 1 farad and 1.2 farad supercaps as battery backups. Basically, I did a system that needed to have a battery backup, and we used a chip in there that had 2 battery backup inputs. So there was like a main battery and an auxiliary battery. And what we did is we put the main battery as a supercap. So it's called a supercapacitor. It's basically a very high capacitance capacitor. And then as the backup battery, we put a lithium, 3.6 volt lithium battery. And the idea was that we figured out that the supercapacitor could keep the memory alive for about 2 weeks at normal temperature range. Like if it wasn't too cold or too hot, it could keep it for about 2 weeks. And then after that, if the thing stayed turned off for more than 2 weeks, then the backup chip, the supervisor chip, would use the battery, the lithium battery. And the lithium battery was not rechargeable. It was just a, use it kind of battery, discharge only, whatever you want to call it, a non-rechargeable battery. And it would last a couple of months, usually, depending on how and what kind of shape it was in when it started and various other factors. So, okay. I'm sorry, I must have done half that out of frame. Okay, so you can see the board looks real skeezy and scummy now. It's pretty gross. But it's actually not that bad. What I'm going to do is I'm going to take this into the other room and I'm going to wash it, clean it. I'm not going to wash this board because this board is going to get a bunch of connectors on it, and I'm going to have to wash those connectors. So I'm going to wash this one first so that I can come back and do all the connectors. So, please wait. You guys can watch my flex pen while I'm gone. You can watch my cutters too. All right, be right back. Yeah, 16, SO16. 16. That's the one. Thanks, man. I have returned from the land of the cleaning products. All right. So this is our now cleaned board. And we're going to put the connectors on it here. And then we're going to put the connectors on this board. And I'm going to go wash this, and I'm going to go assemble these guys off camera, and then we'll be done. So once we have all the connectors on this, then we're finished. So, connectors. What kind of connectors, I hear you ask? All three of you. Well, all three of you, the connectors that we're going to be using are these. These are 1/4-inch phone jacks. They're typically used for guitar type products. So here's a 1/4-inch plug and a phone jack, and they mate like this, very nice. These are stereo, so they have, this is the tip, ring and sleeve. And we have these custom made for us. They're made to our specs. I don't know that that was a great use of my dollars, but it is really nice to have the exact part that I want. So I'm just going to trim these guys. What's up, man? Are those SSOPs? No, those are SSOPs. I already have a bunch of those. So, but those other ones will be here like Thursday, right?
Yeah, Thursday, Wednesday, hopefully.
Okay. All right, I was just talking to my lead henchman, Mitch. We're ordering parts so that we can build the next run of these. So we should have the parts here pretty soon. Okay, so I've been using this fine tip. And this fine tip is not going to be sufficient for putting these connectors in. And actually, you know what? Let's do one thing before we do that. Let's put in the LED display modules. Let's do that. Okay, so this is the LED board here. It has a single driver chip on it, and then it just has a cap and some bunch of pads. So this uses a chip made by Holtec that's job is to, it's like a lot like a 7219. Its job is to multiplex LEDs. That's literally all it does. It just multiplexes LEDs. Alright, so this guy's going here like so. Alright, so we'll put these guys on here and we'll try to get them together so that they look right. And this is not a real big deal. Okay, so I'm just going to solder all these guys on here like so. Never trust anyone who spends more time wiping their iron than they do soldering. That means they don't know what they're doing. How often should you wipe your iron? Well, you either know or you don't know. I wipe mine as little as I can because the stuff that's on the iron will protect the tip from oxidizing. And if you have a little bit of molten solder already on your tip, then that will aid you in conducting heat to the pad. Now, basically when I'm soldering, you can feel the solder push against you. So when I hold this on the pad and I heat it up, I can push the solder in. And if the solder kind of pushes back or makes like a little farting noise, it's not even one you can hear with your ears, but you can feel it in your bones, and you can hear this sort of little farting like if it does that, then I wipe, because that means I'm not getting heat to the pad. Now, I'm going to put my iron back in the holder, and I'm not going to wipe it. Why am I not going to wipe it, you ask? Because the stuff that's on that iron is protecting the iron tip from oxidizing. And the oxygen is going to eventually coat the tip in a thin layer of oxide, copper oxide, a bunch of other oxides. And the oxides are not good conductors of heat. So that as your tip oxidizes, it conducts heat less and less. You have to turn your iron up hotter and hotter to achieve the same joint. And eventually you'll get dry solder joints or cold solder joints, and your stuff will not be as cool as if it didn't have those problems. So when do you wipe your iron? Not when you put it away, but rather when you pick it back up to use it. When I pick it back up to use it, I'm just going to give it a quick wipe, and then I'll use it, and then I'll put it away. Okay, so this one is done. So the display board is now complete, and he's done. And now I'm going to solder on the connectors on this board. This is the upper jack board. There's going to be a capacitor that lives over here on the other side, but I don't have it right now. It's over in the other room, and I need to put it on when everything's done anyway, so I'll do that off camera. But I'm going to put on the DC power jack and then these 4 phone jacks. And in order to do that, I need to swap out this tip for one that is a little bit bigger, physically a little bit larger. So here's my tip, and we're going to take it out of here. Now, you might ask yourself, is the big tip hotter? And no, it's not. It's not about temperature. It's about heat. So the analogy that I was taught when I was in school was that temperature and heat are different things, and they are. Something that's high temperature could be something like a match or a candle flame. Those are both quite hot, but they don't necessarily have a lot of heat. Heat is all about how much energy is present, not about the actual temperature. So you could have a cup of water, of hot water, that's not boiling, and it might have more heat energy than, you know, something that's much, much hotter. So heat energy is measured in calories, which, surprise, surprise, the same exact things that people measure food energy in, calories, exactly the same. It's heat energy. So in America, we just use calories. In Europe, they use kcal, which is the actual and correct unit, kilocalorie. We just use calorie, but we mean kilocalorie. We mean 1,000 calories. So when we say calorie, we mean 1,000 calories, and when the Europeans say kilocalorie, they mean 1 American calorie, which explains why all of our food is so fattening. Because we think we're eating 1,000 times less calories than everyone else. Sorry, dumb rant. Okay, so what I've done is I've swapped out my fine tip for a big fat one, and they're going to be the same temperature, but the big fat one has a lot more heat energy, which is going to let me apply heat energy to the big pads. So these pins on these jacks have a lot of mass. They're much like this thing. This resistor is so light, I can't even tell if it's in my hand unless I rub it. But these jacks have a lot more metal than that. So, quick pull and wipe on this guy, and I'm just going to go just real quickly across the front of each one, and then I'll come back up the middle. And what I'm trying not to do is get any one jack too hot. These jacks are made of glass-filled nylon. It's a PA66, and they're pretty heat resistant. But if you heat up the pins on them, the pins can slide around, and you can end up with some pins taller than the others, and they won't make a contact. And it's just easier to just go across the line. And I'll know that I got everybody because I went across the line. I didn't miss anybody. All right, so this guy is now done. So this upper jack board is now complete, and we're going to need to take it into the other room and wash it, and then we're going to need to put, actually, I'm going to put the header pins on it right now. We have 9 and 4. Actually, I'm not going to do that because I need to wash this. I'll put the header pins on the other side first because I don't have to wash that side. Okay. I guess I do. Yeah, I have to wash everything. Okay, this one is done, and it's actually been washed and everything, but I do have to put these 4 phone jacks on here, and I have to put the pins on as well. So I can do that. These 4 go on here. And now I have that, and they'll need to be soldered. Now this board already has the bootloader programmed, and I've tested the USB, so I know that works. Now if anything else doesn't work, it's probably a solder issue, because I've verified that it's alive and that it can be programmed. And what that will let me do is go and plug it into my computer and upload some development code, and I'll be able to do some tests. I'll be able to talk to it, send it data back and forth, query it, say, hey, are you alive? And it'll say yes or no. Well, it'll say yes, or it won't say anything, and that means no. Okay, so those guys are all soldered. Now I need to put the header pins on. So I have 4 pins here, and this is a sill header, it's just a strip, and then I have 8 pins here. 1, 2, 3, 4, 5, 6, 7, 8. So 2, 4, 6, 8. Okay, so put these guys on here, and I'm not going to solder them all. I'm just going to solder one pin, and I'm going to put some solder in it, and then I'm going to hold the board like this and kind of rock it back and forth until it stands up straight. That way I know I got the header in there straight. Okay, same thing with the other one. I'm just going to solder 1 pin, and these are a little tricky because the jacks are sitting on top of them, and we don't want to melt the jacks. See, I got that one on there super cattywampus, so I'm just going to heat that pin up and lean him up straight as I can. There we go. Alright, so he's on there. Alright, so now all my boards are complete. This concludes our live stream. I hope you have enjoyed it. If you would like me to do more live streams like this, please let me know in the comments. I'm going to leave this up on the channel for anybody to watch it. If this is something you're into, I know not everybody's into watching people solder and run their mouths and talk junk, but hopefully some of you guys are. Again, this is something that I have to do as part of my job. Not the streaming part, but the building of the prototypes. And I really like it. It's therapeutic, it's fun. Sometimes it's frustrating if something doesn't work, or if things don't go my way, or if I'm missing a part or break something. But if everything goes right, it's really fun and rewarding for me. And I figured as part of the goal that I have for 2019 is creating more content. So I wanted to put this up and let you guys watch it. So you can insight into my process. This is kind of the stuff that we do here. So thanks for watching. Click like and subscribe, and I'll see you guys in about